Welcome to our in-depth exploration of one of the most revolutionary discoveries in physics, Ernest Rutherford's nuclear model of the atom. Today we'll discover how Rutherford's gold foil experiment revolutionized our understanding of atomic structure, revealing the existence of the atomic nucleus. Let's begin by understanding the scientific landscape at the turn of the 20th century. By 1900, scientists had established that atoms existed and contained negatively charged particles called electrons, discovered by J. Thomson in 1897. However, the internal structure of atoms remained completely mysterious. How were these electrons arranged? What balanced their negative charge? Here's a fundamental question. If atoms contain negative electrons, what provides the positive charge to make atoms electrically neutral? J. Thomson proposed an answer known as the plum pudding model. The plum pudding model imagined the atom as a sphere of uniformly distributed positive charge, with electrons embedded throughout like plums in a pudding. In this model, positive charge was spread uniformly throughout the entire atomic volume, with radius approximately 10 to the negative 10 meters. Electrons were thought to be scattered randomly within this positive sphere, held in place by electrostatic attraction. The atomic radius was known to be approximately 10 to the negative 10 meters, or 1 angstrom. What did the plum pudding model predict about particle scattering? Alpha particles are helium nuclei, positively charged particles with mass about 4 atomic mass units, much heavier than electrons. An alpha particle has mass approximately 7,300 times that of an electron. According to the plum pudding model, when alpha particles pass through atoms, they should experience only small deflections because the positive charge was spread out. The model predicted scattering through tiny angles, much less than 1 degree, because there was no concentrated positive charge to cause large deflections. Mathematically, the expected scattering angle theta was much less than 1 degree. But here's the critical question. What would happen if experimental results contradicted this prediction? That would force a complete rethinking of atomic structure. In 1909, Ernest Rutherford, along with Hans Geiger and Ernest Marsden, designed a brilliant experiment to test atomic structure. The experimental setup was elegantly simple. A radioactive source emitted alpha particles toward a thin gold foil with detectors positioned around to measure scattered particles. The gold foil was extraordinarily thin, only about 400 atoms thick, approximately 400 nanometers or 0.4 microns. The foil thickness was approximately 4 times 10 to the negative 7 meters. The alpha particles had kinetic energy of about 5 mega-electron volts, making them quite energetic and able to penetrate matter. 5 mega-electron volts equals approximately 8 times 10 to the negative 13 joules. When Rutherford and his team analyzed their results, they discovered something completely unexpected. First, the vast majority of alpha particles, more than 99.9%, passed straight through the gold foil with little or no deflection. This suggested that atoms are mostly empty space, with alpha particles traveling through without encountering significant obstacles. But here's the shocking discovery. A tiny fraction of alpha particles, about 1 in 8,000, were deflected through angles greater than 90 degrees. Some particles even bounced straight back, scattered through angles exceeding 90 degrees, even approaching 180 degrees. The probability of scattering through angles greater than 90 degrees was approximately 1 in 8,000. Rutherford later said this was the most incredible event of his life, comparing it to firing a 15-inch artillery shell at tissue paper and having it bounce back. Let's understand quantitatively why large angle scattering was impossible according to the plum pudding model. The deflecting force comes from the Coulomb electrostatic repulsion between the positive alpha particle and positive charge in the atom. The Coulomb force equals K times Q, 1 times Q2, divided by R squared, where K is Coulomb's constant. In the plum pudding model, positive charge is spread over the entire atomic volume, with radius approximately 10 to the negative 10 meters. Inside a uniform sphere of charge, the electric field at distance r from the center equals ρh(OR) divided by 3 epsilon 0, where ρh is charge density. The maximum force an alpha particle experiences occurs at the atomic radius, approximately 10 to the negative 10 meters. The maximum force is approximately 2e times ze divided by 4 pi epsilon 0r squared, where z is atomic number and e is elementary charge. For gold, The atomic number Z equals 79, meaning 79 protons worth of positive charge. We can estimate the deflection angle by calculating the transverse momentum impulse as the alpha particle passes through. The transverse momentum change equals the integral of perpendicular force over time, approximately average force times 2r over versus. The scattering angle theta approximately equals transverse momentum change divided by total momentum. For 5 mega-electron-volt alpha particles passing through gold atoms according to plum pudding model, the predicted scattering angle is approximately 0.01 degrees, completely negligible. Even if an alpha particle passes through hundreds of atoms, multiple small random deflections cannot add coherently to produce deflections of 90 degrees or more. This raises the critical question: how can we possibly explain the observed large angle scattering? The plum pudding model simply cannot account for it. Rutherford's brilliant insight was that the large angle scattering required a completely different atomic structure. Rutherford concluded that all the positive charge and most of the mass must be concentrated in an extremely small, dense nucleus at the center of the atom. In Rutherford's nuclear model, the atom consists of a tiny, dense, positively charged nucleus, with electrons orbiting in the surrounding space, which is mostly empty. This explains why most alpha particles pass straight through. The atom is mostly empty space, so there's nothing to deflect them. But occasionally, an alpha particle passes very close to the nucleus and experiences an enormous electrostatic repulsion, causing large angle scattering. Rutherford developed a quantitative formula to describe the scattering probability as a function of angle. The scattering is pure Coulomb, scattering from a point-like nucleus containing all the positive charge. The force between alpha particle with charge 2e and nucleus with charge Ze equals 2k Ze squared divided by r squared. Under this inverse square force law, the alpha particle follows a hyperbolic trajectory, as in planetary motion, but with repulsion instead of attraction. The scattering angle depends on the impact parameter b, the perpendicular distance between the incoming particle path and the nucleus. Smaller impact parameter means closer approach to nucleus and larger scattering angle. The relationship is tangent of theta over 2 equals k Ze squared divided by 2 times kinetic energy times impact parameter. From this, Rutherford derived his famous differential scattering cross-section formula. The differential cross-section equals kZe squared over 4e alpha quantity squared times 1 over sine to the fourth of theta over 2. Notice the extremely strong angular dependence, 1 over sine to the fourth of theta over 2. This means large angle scattering is rare, but definitely possible. From the scattering data, we can estimate the size of the atomic nucleus. Consider an alpha particle making a head-on collision with the nucleus. At closest approach, all kinetic energy converts to electrostatic potential energy. Energy conservation gives kinetic energy equals 2kZe squared divided by R minimum. Solving for R minimum, it equals 2kZe squared divided by kinetic energy. Let's calculate this for 5 mega-electron-volt alpha particles scattered by gold nuclei. Plugging in, k equals 9 times 10 to the 9th, Z equals 79, E equals 1.6 times 10 to the negative 19, energy equals 8 times 10 to the negative 13 joules. This gives R minimum approximately 4.5 times 10 to the negative 14 meters, or 45 femtometers. The nuclear radius must be smaller than this value. Modern measurements give gold nucleus radius about 7 femtometers. The ratio of nuclear radius to atomic radius is approximately 10 to the negative 14 over 10 to the negative 10, which equals 10 to the negative 4. This means the nucleus is about 10,000 times smaller in radius than the atom is. Since volume scales as radius cubed, the nucleus occupies only about 1/trillionth of the atomic volume. The volume ratio is approximately 10 to the negative 12, truly remarkable. How did Rutherford verify that his model was correct? Let's examine the consistency checks. Rutherford's formula predicted the exact number of alpha particles that should scatter into any given angular range. Hans Geiger and Ernest Marsden carefully measured the scattering rate at many different angles, from a few degrees up to 150 degrees. The experimental data matched Rutherford's theoretical prediction beautifully across the entire angular range, confirming the nuclear model. They tested the theory with different target materials: silver, copper, aluminum. The scattering scaled perfectly with z² as predicted. The number of scattered particles at any angle is proportional to z², exactly as predicted by the formula. They also varied the alpha particle energy. The scattering rate scaled as 1 over energy squared, again perfectly matching predictions. Number of scattered particles is proportional to 1 over energy squared. Rutherford's discovery had profound implications for physics and our understanding of matter. First, it definitively established the nuclear model. Atoms have a tiny, massive, positive nucleus with electrons in the surrounding space. Second, it opened the entire field of nuclear physics. If nuclei exist, what are they made of? How do they behave? Rutherford himself went on to discover the proton in 1919 by bombarding nitrogen with alpha particles. James Chadwick discovered the neutron in 1932, completing our basic picture of nuclear composition. We now know the nucleus contains protons and neutrons, collectively called nucleons, bound together by the strong nuclear force. But Rutherford's model raised a new puzzle. If electrons orbit the nucleus like planets, classical physics says they should radiate energy and spiral into the nucleus in a fraction of a second. This paradox led Niels Bohr to propose his quantum model in 1913, which eventually evolved into full quantum mechanics by the mid-1920s. Let's examine what we now know about nuclear properties from a modern perspective. We now know that nuclear radius follows an empirical formula based on the mass number A. Nuclear radius equals R0 times A to the 1/3 power, where R0 is approximately 1.2 femtometers. R0 equals approximately 1.2 femtometers, or 1.2 times 10 to the negative 15 meters. This cube root dependence means that nuclear density is approximately constant, independent of which nucleus you're considering. Nuclear density is approximately 2 times 10 to the 17 kilograms per cubic meter, an almost incomprehensibly large number. Here's a question to grasp this. How does nuclear density compare to ordinary matter? Water has density about 1,000 kilograms per cubic meter. The ratio of nuclear density to water density is approximately 2 times 10 to the 14. Nuclear matter is 200 trillion times denser than water. To put this in perspective, a sugar cube of nuclear matter would have mass roughly 1 billion metric tons. Rutherford scattering has been extended and refined in many ways since the original experiments. Quantum mechanics introduces corrections to the classical Rutherford formula, though these are small for the original experiments. At very high energies, the nucleus can no longer be treated as a point charge. Its internal structure and finite size become important. Physicists use form factors to characterize the detailed charge distribution inside nuclei, measured through high-energy scattering experiments. In the 1960s and 70s, deep inelastic scattering experiments at very high energies revealed that protons and neutrons themselves have internal structure containing quarks. Modern particle physics reveals that protons contain 3 quarks, 2 up quarks and 1 down quark, bound by gluons. The basic principle of Rutherford scattering, using high-energy particles to probe structure, has been applied at many scales, from nuclei down to quarks. Let's appreciate the experimental challenges that Geiger and Marsden faced in performing these measurements. They had to detect individual alpha particles, which required sitting in the dark for hours to adapt their eyes, then counting tiny flashes on a zinc sulfide screen. At large scattering angles, the counting rate was extremely low, sometimes just a few particles per hour, requiring patience and careful statistics. They had to control for background radiation, multiple scattering effects, and ensure the geometry was precisely known. The foil had to be thin enough that multiple scattering was negligible, yet thick enough to give measurable scattering rates. Detecting rare large-angle scattering events required understanding statistical fluctuations and ensuring they had enough data for meaningful conclusions. Beyond the specific physics, Rutherford's experiment teaches us important lessons about scientific methodology. First lesson: rare events can be absolutely decisive in science. The 1 in 8,000 particles that scattered at large angles overturn the prevailing model. Second, making quantitative predictions allows critical experimental tests. Rutherford didn't just say large angle scattering proved a nucleus. He predicted the exact angular distribution. Third, sometimes the simplest experiments have the most profound implications. The apparatus was conceptually simple, but the conclusions revolutionized physics. Fourth, scientific anomalies drive progress. Results that disagree with predictions aren't just errors to be dismissed, but opportunities for discovery. Let's work through a quantitative problem to solidify our understanding. Problem: calculate the minimum impact parameter that will cause a 5 mega-electron-volt alpha particle to scatter at 90 degrees from a gold nucleus. Using our formula, tangent of 45 degrees equals kZe squared divided by 2e alpha b. Since tangent of 45 degrees equals 1, we have 1 equals kZe squared divided by 2e alpha b. Solving for b equals kZe squared divided by 2e alpha. Substituting values. K equals 9 times 10 to 9th. Z equals 79. E equals 1.6 times 10 to negative 19. E equals 8 times 10 to negative 13. This gives B approximately 2.3 times 10 to the negative 14 meters or 23 femtometers. Notice this impact parameter is comparable to the distance of closest approach we calculated earlier, which makes physical sense. Let's summarize the key points of Rutherford's revolutionary discovery. Rutherford's gold foil experiment revealed that atoms contain a tiny, dense, positively charged nucleus, overturning the plum pudding model. Large angle scattering of alpha particles was completely impossible according to the plum pudding model, but naturally explained by the nuclear model. The quantitative agreement between Rutherford's scattering formula and experimental measurements across all angles, energies, and target materials was decisive. The nucleus is approximately 10,000 times smaller in radius than the atom, confirmed by subsequent experiments. This result was confirmed by subsequent experiments and remains a fundamental property of atomic structure.